So welcome to the second lecture for reinforcement learning, dynamic programming. So in the last lecture we actually introduced the problem of reinforcement learning. We got to know the agent environment interface and how we define problems to solve with reinforcement learning. And we also introduced our formal framework known as Markov decision processes. Markov decision processes lets us define the environment through a set of states and a set of actions, and we define an agent that actually takes actions in the environment to behave optimally in this situation. We actually also introduced the notion of rewards. So actually this is what the agent actually gets from the environment. There is no supervised learning goal or something like this. The agent simply interacts with the environment and gets a set of rewards. We ended up the last lecture with a definition of our optimization objective, which is basically the optimization of cumulative discounted rewards, or the return. The return is actually a discounted sum of rewards that the agent actually observes until from the start of some episode or some problem until the episode terminates, or like the problem still runs. So this is actually a formulation of what the agent wants to observe, and as we are actually the question is, how can he actually maximize anything inside acting the environment is over the selection of actions. And we then reformulated our goal to say, okay, we want to not optimize the return we get from the environment, we want to optimize a policy that maximizes the return. So we actually want to find a policy that is a mapping from states to actions that tells us how to behave optimally in our MDP, so we get the maximum out of it. Okay, so this was what we did in the last lecture. So in this lecture we actually want to solve such MDPs. So given a formal description of an MDP, we actually want to solve it, meaning that we want to get a controller, a policy that helps us to select optimal actions in any of the states we might encounter. And one of the methods to actually solve such MDPs is based on dynamic programming. And what is actually dynamic programming meaning? Dynamic programming is nothing really special related or terminology for reinforcement learning. It's rather standard computer science terminology that you might also know from solving the knapsack problem, or if you have some experience in machine learning classes, also algorithms such as the Vitali algorithm that you know from hidden Markov models is an algorithm that makes use of dynamic programming. Yeah, so what does dynamic programming actually mean? Dynamic programming actually means that we have an optimal substructure. That means that in our case, basically, it means that if we have a trajectory from a start to an end, and we say that this trajectory is meant to be optimal, then any point on this trajectory, if you select any point on the trajectory from the start to this point within the trajectory and from the point within the trajectory to the end is also optimal. So actually these two optimal trajectories constitute to the optimal trajectory for your environment. This means that your problem satisfies an optimal substructure, meaning that an optimal trajectory can be broken down into two optimal subtrajectories. In this also from this also follows that if you solve half of the trajectory, this helps you to constitute the full trajectory estimation problem. And the second one is that you might also remember, for example, for the Vitali algorithm, or also for solving knapsack problems, that you need some way to cache intermediate solutions, like having a table that helps you to being updated and working on this information all and over again, and actually incrementally making your solution better is also something that you know from dynamic programming. Yeah, and actually it turns out that Markov decision processes satisfy all of them. And what we see in a minute is the so-called Bellman equations, and the Bellman equations break them down into exactly that. Okay, now I have talked much about this. There is Richard Bellman. He actually was very important for the community in reinforcement learning, and he actually introduced the principle of optimality for an agent in the environment, and it just says that an optimal policy has the property that whatever the initial state and the initial decision are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. Which is actually a little bit formal what I just tried to explain. So if you have an optimal substructure and you take the optimal first decision and then you keep being optimal, then you're optimal. So we will see this robot a few times also in the upcoming slides. So if you want to be optimal, take the correct first action, the optimal first action, and then keep being optimal, then you're optimal in your MDP. Okay. But maybe talking about states and rewards and values and optimality, maybe let's start with two simplistic examples. So the first example is just a driving home example, and just consider that you need to go home from your house. You need to go from your house to your workplace, and you want to go as fast as possible. This is something that's really common in practice, of course. You have a set of actions. You can either go left or right, and different actions lead to different road segments. So if you imagine that you are at the crossing and you can go either left somewhere to your workstation, or you can go right, and this also leads you to work. Different actions lead to different road segments, and we define a reward function, which means that it's like the negative time that you need for each road segment. And as you go through your MDP, you will also visit certain states. So actually, imagine that you're working at Google, and you're living in your small house in here, and you have the option either to go over the highway or to take a nice beach experience, and then you can take all over these decisions actually to go to your workplace. And now the question is, how is the reward of each road segment? Okay, let's take that you maybe see in here. I mean, going over the highway is a really quick way to go from A to B. So you get it takes you less time, so you're getting a good reward for it. The beach or the ocean view is taking you a long time. It has other advantages, of course. And you can assign, for each road segment, you just assign like this, time needed to actually go over, or to actually manage to go over the road segment until actually you reach the terminal state, which is in here, your workplace. Okay, and so now what would you actually do to actually get your best route to your workplace? And you maybe also know something like this from early computer science lectures. So actually what you can easily do is to say, okay, so if you go in here, this is your workplace and you take 4 minutes to go over this road, you can actually estimate that if you're being in this road, the reward that you can expect until the end from this state onwards is 4, which is actually it's actually deterministic at this place because there is no decision anymore. So you can actually initialize the value or the reward you get, the return you can experience from these states by just taking the reward you get for the final transition and actually take this as an intermediate cache for your node in here. And you can go on further, of course. So if you now consider the second nodes in here, the question now arises, if you're in this node, the question arises which way to go. So actually, if you're in this node, what is the return you can expect if you are going from here and keep being optimal through the whole rest of your trajectory? And this is simply okay, you actually need just to evaluate to say, okay, I can expect a return of 4 in here, and from here to there I get a reward of 3, meaning that if I'm here and I take the left decision, I can expect a reward of 7 in total. So we're assuming no discount in here. And if I have this node where I can expect a reward of 1, and I get a reward of 5 going this transition, I can in total expect a reward of 6. So actually, if I'm being optimal, I can expect a 7 if I'm taking the right decision at this place. And of course, I can also do this onwards to the root node, where I can say, okay, if I'm at home and I'm acting optimally, I can expect a return of I can expect a reward of 17 in total. So this is actually the principle behind dynamic programming and solving an MDP. In just one example. One thing to mention, or two things to mention at this point. We call the value we put in each of these states, we call this the state value. So actually the return we can expect if we are in this state and keep following our policy. And what we can also do is, depending on this estimation of all these state values, we can also like very easily extract a policy that lets us act optimally with respect to what we just computed. So if you're now actually want to do this and you're actually starting at home and the question is now what to do, I have all the state values. Okay, you just say, if I'm in this place and I have two actions that I might take, what actions gives us the highest return? And in this case it's of course to go left. In this case it's of course to go left, and then we just need to go over this route and then we're at work. So actually, if you have a proper state value estimation for all of your states, extracting a policy that actually lets allow you to be optimal is like a very simple thing to do. So this is one simplistic scenario. We of course omitted a few things, like also probability transition. So there's actions are deterministic. They give us real deterministic successor states. Let's maybe introduce a second example to get all of the contents correctly. So this is the grid world example that I also promised you that you see a lot more often in the future. Like you have a robot and you have a start position and you have some terminal positions. So this is something that you cannot go to. And these are two terminal positions giving you a +1 reward and a -1 reward and 0 reward when you transit through the grid world. And now the question is, what actions to do. So you can say, okay, each of these cells actually constitutes one state, and you have actually 4 actions going up, down, left, or right. Okay, this formally actually describes our Markov decision process, and now let's also talk about the probability transitions. So assume that we are in some state D, probably this one, and you choose to take the action like some action 0. And now the question is, if you are in state D and you take action A, there is probably if the environment is not if the environment is not deterministic, you also have to consider that there is a probability in ending up in different states for different times that you actually select this action in the state. This is the stochasticity we talked about in the last lecture. So assume that taking the same action, we only talk about action A, there is a 30% chance if you start in D and take action A that we end up in E. And there is a 70% chance if you take action A that we end up in state F. Now also assume that we have some estimation of the state value of E and we have some estimation of the state value of F, which is in this case 7 for E and 6 for F. And now the question is, what is the state value of D? And turns out that you can just use some simple math saying that, okay, for taking action A, and if there's no other action involved, the state value that I can that I can assume or that I'm estimating in is like the percentage of times that I end up in state E times the expected value of state E plus the percentage of ending up in F times the estimated state value of F. So I think this is like it's like easy to think of. It's like very natural to think about it like this. So we could also add this probability transitions also to the simplistic example from the beginning with going from home to work example, but it would make things a lot more complicated than there. So okay, so having these two components, we can also formalize this a little bit more. So at this point, we need to introduce some formulas that are actually not that heavy. Maybe if you see them first, they are like look very complicated, but in fact they are not. And we will use these formulas in the upcoming 2 videos as well. And then maybe also they you get a little more native to these formulas. Okay. So we talked about the value or the state as the state value of. So the value of a state, which is basically, which I also said, this is the return I can expect starting from this state and following my policy pi. So actually what we see is, if you follow such a trajectory and you start at some state as 0, you will select an action depending on your policy. So your policy was this mapping from a state to an action, and just assume maybe it's a random policy or it's some other policy. We talk about this in the next videos. And if you're selecting based on the state and action, then you will receive, based on the state and the selected action, you receive a reward. And this is the reward state action reward sequence that you actually experience. So the value of a state S, if you're following a policy pi, is equal to, let's ignore the Q function at this point, but this is equal to what we also saw the last time. It's the expected discounted reward over the state sequence if we start at a state S0 and we keep following our policy. So if we are selecting actions based on our policy and we sum up in a discounted way all the rewards that we get until the end, and we sum this up, this is actually the state value of state S. So we can put it just like this. And for completeness, we will actually derive all the algorithms based on the state value function, but I need also to say there is a state action value function, which is basically a function that is not only depending on S, but also on S and A. So it's basically saying that it's the same concept in the end, but it's saying what is the state action value, so from the combination of being in a state and selecting an action, if you follow a policy pi at this point, which is basically the same, saying that what can I expect if I'm in state S0 and I take the initial action A0 and then I keep following my policy. What can I expect going from that situation? This is actually the same, but it needs you to keep track on every action for each state instead of just keeping track of every value of each state. Yeah, so this is actually the basic state value function and the state action value function, which we also briefly introduced a little bit in the last lecture, but this makes it more formal. And I also talked in the beginning of this video about the Bellman equation. So the Bellman equation was the basic workhorse behind the Bellman principle of optimality, that you can say, okay, I break something down into a substructure. And we can also, this is actually what the Bellman equation tries to do. So the principle of the Bellman equation is to decompose the value function. And because if we are allowed to decompose the value function, we can actually solve our MDP much more conveniently. So we introduced on the previous slide, we introduced the value function of a state S being the discounted sum of rewards of our trajectory. And we can actually break this down. So we can actually say, okay, the value of our state, if the value of our state is the expected return from going now onwards and following our policy, we can also say that if this is the case, our value function state S is nothing else than taking the action that our policy provides, taking the immediate reward from that. So this is actually the reward we get if we are in a state and select an action. And then the discounted sum of values from the next state. So this is actually what we did as we solved the going to work example from the end to the beginning. So actually so we can say that the value of our state is the reward if we go out of our state, plus the values of all these successor states that I might end up in, times the actual probability ending up in these successor states. So this actually combines the intuition that you got from the previous example. So first, going from the back to the beginning, and second, to have these probabilities assigned with it. And this is actually what you put up into this formula. So it's the immediate first step reward that you get, plus the discounted reward that you get from all of these successor states, weighed by their probabilities ending up in there. And this sounds like nothing really important or crucial, but what this actually does, it gives you a system of linear equations. So this forms a system for linear equations, and for each of the state you can build up a formula. And actually what you can do if you build up this formula and you want to have all your variables and all your state values to satisfy these equations, you can just set up the system of linear equations and solve it. You just need to, in the end, you just need to apply linear algebra and solve a matrix inversion problems, and in O of n to the power of 3 you can solve this system of equations. You can do this, but of course there is a better solutions to actually do this, also faster solutions to do this. And what this also says, but you will see this in the upcoming videos, it actually does not give you an optimal policy, it just evaluates your policy. So actually what I did not say so much about it is that where does this initial policy come from? And this lets you evaluate the value that you can expect if you have a policy. So given a policy pi, a controller, you can evaluate the state set, but this does not improve the policy. And this is actually something that we'll do in the next slide, but just for completeness, you can also define the Bellman equation for Q, so our state action value function, given a policy pi, and it's actually really similar, and it's actually like the same as in the value function, because you just put in the Q step and instead of the V function, and you decompose it into the first step return and the subsequent steps. Okay. But actually, if we want to have an optimal policy, and an optimal policy turns out that it looks a little bit different. If you want to define the Bellman equation for an optimal policy pi and an optimal value function V, it turns out that the value of a state S for an optimal policy pi star, this is always what you see a lot, we will call optimal policies pi star and optimal value functions V star. And this looks a little bit different, because actually what we in the beginning did with the Bellman expectation function, what we did is we took the weighted sum of all the values. So actually, what could we expect, like doing this in expectation and all of the times? This is actually the weighted sum of all the probabilities. But if I really want to have the value function of the optimal policy, I'm really only interested in the maximum, in the value of the state with optimizes, with actually returns the maximum return, because this is actually what we want to go to. So if you see that in the first example with the driving home example, we always selected the maximum of the two routes, which is maybe something like intuitive what you would do, because this is actually what you want to. That's actually where you want to go. And it turns out that the optimal, the value function of the optimal policy pi is actually equal to the action that maximizes the immediate reward plus the discounted sum of rewards of the successor states, which is basically what we did in the previous example if we would add the, in the simplistic scenario 1, if we would add the probability transitions in here. So this is kind of doing the same. And this is what we actually want to optimize in the end. However, what you see here is now we just cannot solve it through matrix inversion, because we have a nonlinear operator here, which is the max function, which means that we cannot just easily invert a matrix and solve a system of linear equations. So we need some other methods. Basically, we need iterative methods, and this is why we use dynamic programming to solve it. The Bellman optimality equation can also be defined for Q, like straightforward as we did it in V. However, it's still nonlinear because we have the max operator in here, and they also need an iterative method to solve it. And However, this will be something that we will cover in the next 2 videos. So we will actually find algorithms that solve the Bellman optimality equation and that actually returns an optimal value function or an optimal policy for a given MDP that we have accessible. So, yes, thank you.